All right, so this is going to be the best video on YouTube for how to derive Bernoulli from Navier-Stokes. I did some research and I couldn't find a video that explained it as completely as I'm going to explain it here. I did the derivation, so I'm going to be like writing it over here and then looking back at my notes, but yeah. Cool beans. So step one is to write out Navier-Stokes in just one of the components just for reference. So I'm going to pick the x component, right? Yep. X component. Yep. What does it equal? Okay, that's a Navier-Stokes in one component. There are three components. There's x, y, and z. This is just one of them, and I'm using it as reference because step two is just divide by the density. I'm not even going to write a new line for that. All right, divided by density, cool. Step three, rewrite in vector form. Okay, so we can break this up into a couple different chunks. There's this chunk, there's this whole chunk, this one, and this one. So let's rewrite each chunk in vector form. All right, so the x component of velocity is u, which is what I wrote out here. This should be a dt. But I'm gonna call the vector of velocity v. Even though v is used as the y component, I'm just gonna call it v. So we have it's terrible, dv vector dt. Right? Yes. Okay. Now, this chunk is basically v. Is it dot? What is it? Once I see it, it makes sense. I can explain it. Yeah, okay. Dot grad. It's gonna take a while. Dot grad v, and the reason why v's are in parentheses is because we have u and x, v, y, w, z. If v's were grouped in parentheses, we would have u, x, v, y, w, z, but we don't. U is constant in the x component equation. In the y component equation, u changes, which is why this is also a vector. All right, so we got that term. Now onto the right side. We have gravity as a vector. Grad p, because up here we have dp dx, and in the y we have dp dy, and then in the z we have dp dz. So grad equals d dxi. So here x1 is x, x2 is y, and x3 is z. So there you go. Cool. Last component. Yeah, that makes sense. Okay. Plus u over rho. This whole term can be written as grad squared of v. P is also an arrow. Okay. And grad squared is, what would it be? Squared dxi squared? Something like that. I forgot. That might not be the right thing. I could look at my notes, but I don't really care. This is the correct simplification. Okay. Cool. Rewrite in vector form. Next step is to non-dimensionalize. I'm just going to copy these and move them over. Copy. Paste. So what do each of these mean? To non-dimensionalize, you effectively want to take the magnitude out of each number such that the variables range from like -1 to +1. So you take the magnitude out, basically. So for example, with the velocity, you take the magnitude out. So you just call the largest velocity in the system, you call that u. And every other velocity in the system is a percentage of u, basically. So that's the easiest one. Well, this one also. The largest distance in the system is L, and every other distance in the system is a percentage of L. So the percentage is represented by X with a hat. If there's a hat over it or the bar over it, that means it's non-dimensionalized. Same with gravity. You basically take out the 9.81. This is just the stagnation pressure. This is kind of cheating because I'm using the Bernoulli equation to derive the Bernoulli equation, but I'm just going to let it slide. This one, it makes sense because velocity, well, distance over velocity equals time. So you just take that physics 1 equation and you just use it as a non-dimensionalizing equation. Cool, so now you plug each of these in, right? Sub in non-dimensional values, yes you do, okay. So, the V is a U. So it'll be U, T is L over U, but since it's on the bottom, it's a U over L. Then it would be dV hat, dt hat. Okay, plus second term. Same thing. Why is it the same thing? It is the same thing because it's basically one of these. They're all the same. It's a velocity times a d velocity d distance. So it's a u times velocity over distance. That would be v hat dot grad V hat. Cool. Equals, is that right? Yeah, that's right. Cool. There's sirens outside. They're trying to arrest me because I've discovered the key to physics. Okay. The G would just be, oh dang, would just become G. GG. Game over. I win. Yep. What's next? Pressure. Minus 1 over density. Grad of pressure. That's probably going to be stagnation over distance. Is that what I had? That is exactly what I had. Let's go. Right? Yeah, okay. All right. If you're asking why am I non-dimensionalizing, you'll see in a second. That felt needless to say. This whole thing is a you'll see in a second. The whole derivation is, but okay. Plus u over rho. This last term will be a u over L squared, I think. Yep, a u over L squared. Grad squared V hat. Okay. Cool. Now, I can multiply this stuff out. So I get a u squared over L dv dt plus u squared over L v dot grad. It's a terrible grad, but that's fine. Equals GG. Those would cancel out. Those densities cancel out. Oh, forgot to write pressure. Is that right? That's probably right. Okay. Next step is to divide everything such that the stuff in front of the viscous term, which is this term, equals 1 over Reynolds number. And luckily, to do that, all we need to do is divide by u squared over L. So let's do that. Okay, like I mentioned, this is 1 over Reynolds number. Is that what I have so far? Yep. Cool beans. So then we assume a high Reynolds number to cancel this whole term out. And the reason why that works is because if you have a high Reynolds number on the bottom, since the Reynolds number is in the denominator, it makes this whole term go to 0. And since it's multiplying by this whole term just goes to 0. What does that mean physically, though? So fluid moving around or mixing itself absorbs energy. Like if you just mix water in a cup and you come back a minute later, it won't be mixing anymore. And that's because it absorbs energy and eventually there's no more energy to absorb, so it stops mixing. So this assumption, the idea is if you have low Reynolds number, that means your velocity has very low energy. And that means viscous forces are significant. The viscous forces could be enough to completely stop the motion of the fluid. And if that's the case, Bernoulli equation will not work. But if your Reynolds number is high, if your fluid has a lot of energy, the viscous forces still exist, but we can assume they're negligible because they're pretty small. It's like if you mix your water in a cup like a tiny bit, it'll take less time for it to stop than if you mix the water like a lot. Okay, hopefully I explained that half decently, but that's the assumption behind crossing this stuff out and assuming a high Reynolds number. Okay. That's our first assumption, by the way. And then we can non-dimensionalize. By the way, each of these steps took me like 10 minutes to figure out. Like this is the most preparation I've done for a video ever. Yep, non-dimensionalize. So now we go from these dimensionalized variables back to the vector variables by literally multiplying by the opposite of what we multiplied over here. So let's do that. So it would be L over U squared V vector dt. Yep. Plus same thing again, L over U squared. I'm just doing the opposite of whatever was in front before. I'm gonna move this whole thing down a bit. This would end up putting a G in the denominator. So we'd have the original G, another G in the denominator. So those would cancel out, but I'll wait a second to cancel them out. You'll see why. It's more satisfying if everything cancels out by itself. The pressure is this. So we're gonna do L over rho U squared grad P arrow. This term went away. That is it. Cool. Okay, so what can we do here? We can cancel out L over U squared, L over U squared, L over U squared, G's, L over U squared. So we're left with dV dt plus V grad V. I forgot the G. Minus 1 over density grad P. So in a lot of the videos I've seen, they just assume that the viscous terms go away, which is fine, but they don't explain the reason why they go away. And the reason why is because you have to assume a high Reynolds number. So if you have a low Reynolds number fluid, Bernoulli won't work accurately. So that's kind of why I did all that. But now we're back to normal stuff. So what's the next step? Non-dimensionalize. Did I assume steady? I didn't assume steady state yet. I could have done this from the start, actually. Assume steady state, that the derivative with time goes to 0. Okay, now project along a streamline. So, well, I kind of drew it over here, so I'll just use this picture. So let's say you have a pipe that looks like this, and to use the Bernoulli, you have to pick 2 points along the same streamline. So like you could have 0.1 over here, P1, 0.2 over here, P2. They'll be along the streamline. Yeah. So in order to project Navier-Stokes or any equation along a line, you dot product the equation with the direction of the line. So the direction of the line I'm going to call ds. And the idea is if you integrate ds along x and y, well, z also if there's a third dimension, but in this case just 2 dimensions. If you integrate ds along x and y, then you'll get the full path, the length of the full path. So let's do that. Let's dot product all of the terms in our equation with ds. So we get okay. And we can change this one a bit because with gravity, the only, I guess, direction for gravity that we care about is y, the vertical direction. So we don't care about the x component. So what we can do is change that s to an x. Nope, to a y. My bad. Okay, but these other 2 components we leave as ds. All right, what does this allow us to do? Oh yeah. Okay, well, I kind of explained it over here. So the definition of the gradient, I wrote it over here as well. Did I write the same thing? Yeah, the definition of a gradient is d over dxi, so dx, dy, dz. So if you have like a, well, okay, let's do what we have over here. So we have the v vector. If we do grad of the v vector, then we get du dx. Is that what we got? No, let's not do grad of a vector. That's too complicated. Let's do grad of u, and u is just one component of the v vector, the x component. It would be du dx plus du dy plus du dz. But effectively, we defined ds such that if you integrate it with respect to x and y, you get the full path. So basically the gradient is d ds. Is that what I have? That is exactly what I have. So basically, the gradient cancels out with multiplying by ds. So let's do that. We have a gradient, we have ds, and we have a gradient being multiplied by ds. So those cancel out, which is freaking neat. Okay. What's next? Oh. Okay, so we canceled out those parts, but we still have the du on the top. This doesn't just become u, it's still du. So even though we canceled out the gradients, we have to do v dv. So the derivative of v from this gradient is being applied to that. Dang, I like how clearly I wrote my notes for myself. Very cool. Minus dp. Cool. I think that's correct so far, right? Yep, v, okay, yep. All right, now we can assume constant density. Then we divide by gravity and then we're done. That's it. Okay, so if we assume constant density, right there, we can integrate both sides. Oh, that's terrible. And we end up with v squared over 2. Actually, are these vectors anymore? I don't think they're vectors. I think they're just magnitudes. I think after multiplying by ds, I think it gets rid of the vector sign. So I'm just gonna get rid of them. That might be wrong, but that's fine. So when you integrate this term, you get v squared over 2. When you integrate this term, you just get gy. When you integrate this term, you get negative p over density. Yep. And then to get it into the form that I like, which is the correct form, you just divide by gravity. So you get v squared over 2g equals h. Oh, you can leave it as y. Minus p over rho g. And that is literally it. That is literally it. And the whole idea is this equals a constant. And that is your Bernoulli equation. And the actual Bernoulli, I write it out as this, but it's literally the exact same thing. We just swap h and y, but it's the same thing. But yeah, so I guess going over the assumptions. So high Reynolds number, yep. Constant density, yep, that's how we integrated. Along a streamline, yep, because that's what we did the ds for. SETI, yep, because we canceled out the dv dt. Cool. Again, this was the most perfect Bernoulli derivation video on YouTube. Chances are that what I said is incorrect, that there is a better video out there, but I could not find it. So I'm going to assume that this is the best video. Cool beans.